Dr. R.K. Radha, Assistant Professor, Department of Statistics, Presidency College, Chennai. She has done her PhD in statistics on a novel approach for prior selection in Bayesian modeling. She has 27 years of teaching experience, has guided 4 MPhil students, published 5 articles in national and international journals, has attended 10 conferences in India. She had given training for staff at Tamil Nadu State Statistical Training Institute, Department of Economics and Statistics.
Welcome to UGC lecture series on mathematical sciences. So we are discussing about the topics under statistical inferences, under which we are going to discuss today's class on interval estimation. So what are the topics to be discussed are introduction, that is I am going to discuss about the point estimate and the interval estimate, then to discuss about the confidence interval and the limits, and we are going to derive how to find out the confidence interval for the parameters of normal distributions and few examples. So to start with, already in my previous lectures, all the cases which we are discussing is about the point estimates. In other words, point estimates gives the value, single value of an estimator of a parameter of the population as an estimate of the theta. In other words, whatever values we are getting, it is a single value, hence we define it as a point estimate. But this estimator is not the true value of the parameter and it does not tell the amount of the error. So what is the solution? So here we have got a solution saying that whatever values we have obtained from a given problem, that is from the given sample, the problem is, can we make some reasonable probability statement about the unknown parameter theta in the population from which the sample is drawn. This question is answered by the technique of confidence interval due to Neyman. Now let us discuss the technique of confidence interval due to Neyman. We choose once for all small values of alpha, where alpha is defined as a level of significance. Alpha can be fixed as 5% or 1%, and then determine two constants, say L1 and L2, such that probability of L1 is less than theta is less than L2, which is equal to 1 minus alpha. Now this L1 and L2 are functions of x1 etc. up to xn and hence are random variables. Now let us discuss the definition of confidence limits. The quantities L1 and L2, which is given by Neyman technique, are known as the confidence limits or fiducial limits. So we have to find out L1 and L2. So those are called as the confidence limits. Next, let us define what is the confidence interval. So the interval within which the values lie, L1 and L2, for the unknown parameter is expected to lie is called as the confidence interval. So here without the interval we call it as just the values L1 and L2, that is confidence limit. Within the interval, if the parameter lies, then we call it as a confidence interval. Next we have got a concept called as a confidence coefficient. 1 minus alpha is called as a confidence coefficient. Already I have said that alpha is called as the level of significance, or in other words type 1 error also we can call it as. It is also called the degree of confidence. Now if you take alpha is equal to 0.05 or 0.01, then the degree of confidence is 0.95, or if you take for 1% it is 99.99, and the interval L1 and L2 is called as the confidence interval. Now we are going to get the confidence interval for the parameters of the normal population. So if x follows normal, you know very well that there are two parameters, namely mu and sigma, standard deviation sigma, or you can also, if you write sigma squared, it becomes a variance. So here we are going to find out the parameters mu and sigma squared for the parameter of the normal population. So first let us go for the confidence interval for the mean of the normal population. So let x1 etc. up to xn be a random sample from the normal population where mu is unknown and sigma squared, the variance, is known. We know that z is equal to x bar minus mu divided by sigma by root n follows a standard normal variate, that is n of 0 comma 1. Mu is 0 and your variance is equal to 1. We call it as a standard normal variate. Now confidence interval we have to find out. So here hence the confidence interval with the probability 1 minus alpha is given by probability of minus z alpha by 2 less than or equal to z, which is less than or equal to z alpha by 2, which is equal to 1 minus alpha. Now replace z. Z is nothing but x bar minus mu divided by sigma by root n, so which is equal to 1 minus alpha. Simple steps we are going to do is that multiply either side by sigma by root n, so that is what I have done here. Then subtract x bar on the either side. So here on subtracting you will get it as minus x bar minus z alpha by 2 less than or equal to, this becomes 0, you will have it as minus mu less than or equal to minus x bar z alpha by 2 sigma by root n. Then multiply throughout by mu minus 1, then what happens is that inequality get reversed and you will finally end up with x bar minus z alpha by 2 into sigma by root n less than or equal to mu x bar plus z alpha by 2 sigma by root n, which is equal to 1 minus alpha. So this is the confidence interval for mu when sigma squared is known. Now we have got two notes, namely that for large samples, so large samples are declared when the sample size are greater than 30. So if n is greater than 30 and if your sigma is known, that is your standard deviation is known, then you can replace sigma by sigma cap, hence the confidence interval will become x bar minus z alpha by 2 sigma cap by root of n comma x bar plus z alpha by 2 sigma cap by root n. So here you have to find out the table value using the normal tables, substitute what is your sigma cap n x bar, you will get the required confidence interval if the sample size is large. For small sample statistics, sigma is unknown. Therefore, you have to consider this statistic of the form t is equal to x bar minus mu divided by s by root n follows t distribution with n minus 1 degrees of freedom, where my capital S squared, that is nothing but my population variance, which is you know that expectation of S squared is equal to sigma squared. It is an unbiased estimator of population variance, which I can write it as 1 by n minus 1 summation xi minus x bar, since I have to my mu is unknown. Okay. Now this distribution has a t distribution with n minus 1 degrees of freedom. Therefore, my confidence interval can be written as probability of minus t alpha by 2 less than or equal to x bar minus mu s by root n, that is minus probability of minus t alpha by 2 less than or equal to t less than or equal to t alpha by 2, which is equal to 1 minus alpha, replacing t by x bar minus mu by s by root n, which I have already defined here. Now you are going to repeat the same steps like multiplying either side by s by root n, then subtracting throughout by x bar, then multiplying throughout by minus 1, inequality gets reversed. Finally, you will end up with probability of x bar minus t alpha by 2 s by root 10 less than or equal to mu less than or equal to x bar plus t alpha by 2 s by root 10, which is equal to 1 minus alpha. Therefore, 100 into 1 minus alpha percent confidence interval for the population mean is x bar minus t alpha by 2 s by root 10 comma x bar plus t alpha by 2 s by root 10. Already I have defined in my definition, this is nothing but my L1 and L2, where these are the constants which you have to find out, and if you substitute, then we can say that it is the confidence interval or limits. Next, we have to find out the confidence interval for the parameter sigma squared of the normal populations. So, already we have found out what is the confidence interval for mu with two cases when sigma squared is known, sigma squared is unknown. Here we are going to find out the parameter for sigma squared under two conditions, namely that mu is known and mu is unknown. If mu is known, then you consider summation xi minus mu the whole squared by sigma squared. So, this part you can write it as ns squared. Then you know that your s squared can be written as 1 by n summation over I xi minus mu the whole squared. So, this particular part is nothing but ns squared follows sigma divided by sigma squared is nothing but follows a chi squared with n degrees of freedom. So, actually the chi squared statistic is nothing but the sum of squared of a standard normal variate. So, hence this follows a chi squared with n degrees of freedom. Now, I am going to define chi squared of alpha as the value of chi squared such that probability of chi squared greater than chi squared alpha is nothing but integral chi squared of alpha to infinity probability of chi squared d chi squared, which is equal to alpha, where probability of chi squared is nothing but probability density function of chi squared distribution with n degrees of freedom. Now, we have to find out the confidence interval. So, the required confidence interval is nothing but probability of chi squared 1 minus alpha by 2 less than or equal to chi squared less than or equal to chi squared alpha by 2, which is equal to 1 minus alpha. So, replace chi squared by ns squared by sigma squared. So, multiplying throughout by ns squared and replacing 1 by sigma squared, you get this particular operation, that is probability of ns squared by chi squared alpha by 2 less than or equal to sigma squared is less than or equal to ns squared by chi squared 1 minus alpha by 2, which is equal to alpha, where chi squared alpha by 2 and chi squared 1 minus alpha by 2 are obtained from chi square tables using n degrees of freedom. Therefore, 100 into 1 minus alpha percent confidence interval for sigma squared is nothing but ns squared by chi squared alpha by 2 comma ns squared by chi squared 1 minus alpha by 2. So, s squared you can find out and n you can find out. You can refer from the chi square tables with appropriate degrees of freedom, and if you substitute you can find out what is your L1 and L2. Next, we are going to discuss the second case. Mu is unknown and we are going to find out the confidence interval for sigma squared. In this case, since mu is unknown, we have to estimate mu, which is given by x bar. Therefore, summation xi minus x bar the whole squared by sigma squared again is nothing but ns squared by sigma squared follows chi squared with n minus 1 degrees of freedom. Since we are estimating our x bar, that is we are finding out mu, because mu is unknown, your degrees of freedom will become n minus 1 degrees of freedom. Therefore, 100 into 1 minus alpha percent confidence interval for sigma squared is nothing but ns squared by chi squared alpha by 2 comma ns squared chi squared 1 minus alpha by 2. where this chi-squared alpha by 2 and chi-squared 1 minus alpha by 2 are obtained from chi-square tables by using n minus 1 degrees of freedom. So, coming to the degrees of freedom is nothing but number of independent observations. Let us go to the first example. So, a simple random sample of size 100 has a mean 15 and the population variance 25. You have to find out an interval estimate of the population mean with the confidence interval 95% and 99%. So, two confidence level you are going to find out, that is if alpha is equal to 5% and alpha is equal to 1%, you have been given size as 100. So, that makes you that it is a large sample, because I have said that if sample size is greater than 30, then it becomes a large sample. Hence, your mean is given as 15 and the population variance is 25. That is, you are given n is equal to 100, x bar is equal to 15, sigma squared is equal to 25, therefore, your sigma is equal to 5. Now, you have to find out the 95% confidence interval for the population mean. So, you have been given the formula, namely that x bar plus or minus z alpha by 2 sigma by root n. Z is nothing but you have to refer the normal tables. Now, from the normal tables, alpha is 5%. So, it is 0.05, alpha by 2 will become 0.025 for two-tailed test. Therefore, Z alpha by 2, when you refer normal tables, it will become 1.96. So, Z alpha by 2 is 1.96, x bar is 15, sigma is 5 and your n is 100. So, 5 divided by root 10, root 100 is 10. So, on simplification it gives you 0.5, multiply with 1.96, it gives you 0.98. So, add up with 15. So, 15 plus 0.98 gives you 15.98. On subtracting 15 minus of 0.98, you get 14.02. Therefore, my 95% confidence interval for my mean mu is 14.02 comma 15.98. Here my sigma is known. Next, I have to find out 99% confidence interval for the population mean. So, coming to the thing, here the same formula, but here you have to change the table, that is alpha is 1% means alpha is 0.01, alpha by 2 is nothing but 0.005. Therefore, Z alpha by 2 will become 2.58. So, substituting here in the same manner, only change comparing to the previous section is that your table value. So, 15 plus 1.29 gives you 16.29 and 15 minus 1.29 gives you 13.71. Therefore, my 99% confidence interval for mu is nothing but 13.71 comma 16.29. So, in example 1, I have taken a situation where sample size is large and I have to find out the confidence interval for mu, sigma is known, and I have discussed for the two case, namely that 95% and 99%. Now, this is an example for a small sample. So, let us go through the example. A fertilizer mixing machine is said to give 12 kg of nitrate for every quintal bag of fertilizer. 10 100 kilogram bags are examined and percentage of nitrate is as follows. So, you have been given 10 observations, namely 11, 14, 13, 12, 13, 12, 13, 14, 11 and 12. You have to obtain 95% confidence interval for mean. So, here 95% confidence interval for mean if the sample size is small. that is when n is less than 30 is given by x bar plus or minus T alpha by 2 for n minus 1 degrees of freedom s divided by root n minus 1. There are two options. If you take capital S divided by small n, if you take small s, you divide it by n minus 1. So, here you have got a preference also to use this, that is here when your sigma is known, you can take here. When you are going to estimate, it is better that you use s by root n minus 1. So, from the given sample observations, that is from these 10 observations, we find that n is equal to 10, summation x is 125, x bar, that is x bar is defined as 1 by n summation of x, which is 125 divided by 10, which gives you 12.5. Your small s is nothing but summation x squared by n minus your x bar the whole squared. So, summation x bar squared from the given data is 1573, n is 10, then your x bar is 12.5. Substituting, you find that your s is nothing but 1.025. Now, you have to get the value of T alpha by 2 with n minus 1 degrees of freedom. So, table value from T distribution using T tables with n degrees of freedom, that is total number of observation is 10, but you are estimating one parameters, totally you will have 9 degrees of freedom at 5% level. When you refer the table, you will get 2.262. So, substituting your n, your x bar, then your s in the given equation, you find that x bar plus or minus table value T alpha by 2 is 2.262, your s is nothing but 1.025, which you have found out here, and root of n minus 1, which is 10 minus 1, which is root 9, okay, which is root 9. So, here root 9 gives you 3. So, on simplification, this particular part 1.025 divided by 3 gives you 0.34, and multiply with 2.262 and add up with 12.5 and do one operation with that. The other operation is that 12.5 minus of 2.262 into 0.34 gives you 11.73 and 13.27. Therefore, 95% confidence limit for the mean is 11.73 and 13.27. So, the second example I have taken based upon your small samples and where your sigma is unknown and you are finding out for the parameter mu. Now, this is the third example, where this third example is the example for your sigma squared when mu is unknown. Okay. So, let us go through the example. Weights in kg of 10 students are given below, that is 38, 40, 45, 53, 47, 43, 55, 48, 52, 49. So, 10 samples are given to you. You have to obtain 95% confidence interval for the variance of the distribution of weights of all the students from which the above sample of 10 students was drawn. So, here coming to the solution, n is equal to 10. Now, in this problem, to make my calculations much more easier, I have taken deviations, where my deviations I have defined as d, that is, in other words, I have taken the origin about minus 47. So, when you say for example, first observation is 38. So, 38 minus 47 will land up with minus 9. So, you do for all the observations, then that will amount for d. So, when you get the column of d, add up d, then find out d squared, sum it up, substitute in this equation, you find that summation of deviation is 0, summation d is 0, so 0 divided by anything is 0, summation d squared you are getting it as 280, n is 10, so on simplification you get your 28 kg squared, which is your ns squared. Now your 95% confidence interval for the variance is nothing but ns squared divided by chi squared alpha by 2 and ns squared divided by chi squared 1 minus alpha by 2. So from chi square table, here from the chi square table you are getting alpha is nothing but 5%, 95%. So here which is 0.05, alpha by 2 is nothing but 0.025, and you need to find out 1 minus alpha by 2, which is 1 minus 0.025, which is 0.975. Now you go in for your chi square tables with the number of observations is 10. So with 9 degrees of freedom, chi squared at alpha by 2, that is 0.025, you will be getting 19.023, and chi squared with 0.975, you will be getting it as 2.700. So this is nothing but my 95% confidence interval for sigma squared. So substitute n, s squared, table value, and see what happens. N is 10, my s squared I have found out 28, here from the table values 19.023, similarly here 10 into 28, here it is 2.700. So do the simplification. On simplifications you will find that the confidence interval 95% confidence limits or your interval for variance is 14.72, 103.7. So here in today's class we have defined what is the confidence limits. So coming to the confidence limits, I have said that the problem lies in interval estimation is to find out the two constants L1 and L2. So here where the parameter lies within the two constants L1 and L2 is defined as the confidence interval, and my confidence coefficient I have said it is nothing but 1 minus alpha, where my alpha is nothing but the level of significance. So usually we use the level of significance as 5% and 1%. More about my level of significance I will be discussing in my next sessions. Next I have derived an expression for the parameter of normal distributions, where there are two parameters, namely mu and sigma squared. I have under the parameter mu, I have discussed the two cases when sigma is known and sigma is unknown. So if sigma is unknown, it follows a t distribution. If sigma is known, then you can use your normal tables with appropriate degrees of freedom. Next, I have said that for the parameter sigma squared, you have two cases here also. Mu is known, mu is unknown. So in both the cases you have to refer chi-square tables. If mu is known, then it's enough that if you find out chi-squared with n degrees of freedom. If mu is unknown, you are estimating for mu, that is your x bar. Hence it follows a chi-square distribution with n minus 1 degrees of freedom, and all these normal tables, your t tables, your chi-square tables is available. So you can refer the table value, take the table value, substitute in the appropriate equations, and you will get the required results. I have discussed one example in each the cases for you. So I have got few questions for you. The first question is that state the difference between the point estimation and interval estimation. So here point estimation means an estimation which gives a single valued function When it is not a single valued, then it has to be within an interval, hence we get the question of interval estimation. Define the confidence coefficient. So, confidence coefficient is nothing but your confidence in determining the value, which is nothing but your 1 minus alpha. Then third question is that you have to obtain 100 into 1 minus alpha percent confidence interval for the parameters of the normal distribution. As I have discussed in summary, you have to discuss two cases. Main case is that for the parameter mu, and the next case is for the parameter sigma squared. Under the parameter mu, you have to discuss the two cases, namely that when sigma is known, sigma is unknown, and when you come to the parameter sigma squared, you have to discuss again two cases, namely that when mu is known and mu is unknown. And finally, remember that you have to identify the problem, whether it is large sample or small sample. If the sample size is greater than 30, we classify it as a large sample, otherwise we classify it as a small samples. Thank you.